So starting chapter 5 here, and one of the big things we're going to make use of in chapter 5 is all these trigonometric identities that we have here. Hopefully you feel like some of these you already know, these reciprocal identities here, probably these quotient ones. You knew that tangent was y over x on the unit circle, and sine was the y and cosine was the x. That should make sense. The Pythagorean identities come from the Pythagorean theorem, as you probably guessed. You can either draw a triangle and look at the Pythagorean theorem and rewrite the values as ratios, do a little bit of algebra to make that work, or just look at how we define things on the unit circle. If you look at, we said that we drew the triangle for this here, drop that down. Well, we called sine the y coordinate of this point right here if we had a radius of 1, if the hypotenuse is 1. So if sine is the y, that's this opposite side right here. And then the x was cosine, that's this adjacent side right here. Well, if you just do the Pythagorean theorem on this triangle here, you'll have that sine squared plus cosine squared is 1. You notice this notation that we use here, we put the squared right next to the trig function right there. We're trying to show the difference between having sine of x squared versus sine of x squared. We don't have to want to always write those parentheses. We're too lazy/efficient to do that. So if we want the whole function to be squared, that's when we put the squared right next to the function. Sine squared of x means sine of x squared. And then if we want the input to be squared, we just don't write the parentheses. If you see sine x squared like that, it's the input of the function that's being squared. Just note a little bit of inconsistency with this notation here. If we say sine -1 of x, that is not the same thing as sine of x to the -1. Of course, this is our inverse trig function here. We also know that as arcsine. But sine of x to the -1, that would be 1 over sine of x. That would be cosecant. So any other number next to a trig function here, it's just an exponent. -1 is an exception. That's why some people like to use the arcsine notation, because of this kind of inconsistency here. We've also got some odd and even identities here. That comes from looking at the trigonometric functions as having either odd or even symmetry. So if you look at sine and tangent, they have odd symmetry. They're symmetrical about the origin. If you look at cosine, it has that even symmetry. It's symmetrical about the y-axis. So we looked at that last semester when things were even. We saw that negative and positive x values have the same y value. It doesn't matter whether the x is negative or positive, but it comes out the same. And so cosine is the one to kind of take note of here. Then cosine is the one that's even, where the negative kind of disappears. Doesn't matter whether you do cosine of -pi or cosine of pi, you're going to get the same exact thing. Odd functions, when you plug in a negative, you get a negative out. Negative x gives you negative y. Those are the ones that that's probably what you would expect, where the negative can just come outside. So it's cosine that you want to really pay attention to, where that negative goes away. So we're going to use all these different identities to try to rewrite these, try to simplify these a little bit. Some guidelines there that we'll talk about more in a little bit. I'll just make a note right now, though. Those are only guidelines. They're not hard and fast rules. It's kind of like Pirates of the Caribbean. They're just guidelines, not rules. So right here, if we take a look at this, we can just multiply this out. What we're going to be doing a lot this chapter is looking at these trig functions as kind of one big whole thing. So remember u substitution, you could look at that as kind of 1 plus u times 1 minus u. Just treat this sine of theta as kind of one chunk, one big variable. And so if I multiply that out, just like this would be 1 minus u squared, this here will be 1 minus sine of theta squared, which we write as sine squared theta. And then we can actually simplify this further. You don't see anything up here that looks exactly like that, but one of our first guidelines is when things are squared, we're going to use those Pythagorean identities. Now I don't have 1 minus sine squared here, but what we do a lot is we take these Pythagorean identities and we rearrange them. So we can manipulate this equation any way we like, move things around to different sides. So here 1 minus sine squared, I could get that. I could subtract sine squared x to both sides and get that cosine squared x is 1 minus sine squared x. So x or theta, doesn't matter what we have inside there. 1 minus sine squared theta, that means this will be cosine squared theta. And so that is our simplified answer right there. All right, and just make sure you note this caveat here, only if it's squared can you use these Pythagorean identities. So if the squareds are not there, that equation is not true. If it's a cubed instead of a squared, it's not true. It's only when those are actually squared. Okay. But, and then for this one here, notice that we have two different sine terms here. And so this is the greatest common factor. We're going to factor these things a whole lot. If you have trouble seeing that, again, think of these as whole big chunks here, each trig function being maybe a variable. You could look at this as maybe a b squared minus a, where you could see that you could factor out a. So here we're going to factor out the sine x. We're going to say sine x times cosine squared x minus 1. And again, we've got this squared here, so that tells us we might be able to use a Pythagorean identity. Just be really careful when you rearrange these here. If I do cosine squared minus 1, if I subtract the 1 to the left side, I have to subtract the sine to the right side again. So cosine squared minus 1 is going to be negative sine squared, not just sine squared. So I'll have sine x times negative sine squared x. And so then sine times sine squared, that's going to give me sine cubed. Just like if you had u times u squared, you'd have u cubed. And so this right here is going to be negative sine cubed x. And that's our final answer. Fine. On this one, anytime we have a negative x inside the trig function, automatically we'll use these odd or even identities. And the question is just whether the negative comes outside or whether the negative disappears. So we know that sine is an odd function. If you think about that graph, it's got symmetry around the origin. So a negative x value gives you a negative y value. So we're going to have negative sine x. And then cotangent is going to behave just exactly the same as tangent. If you looked here, if you plug in a negative x to cotangent, you plug in negative x to tangent right here, 1 over a negative, the whole fraction would be negative. So all these are true for the reciprocal functions. This means cotangent of negative x has to be negative cotangent of x. Secant of negative x would have to equal secant x. Same thing for cosecant. All these will still be true. So here, tangent being odd means that we do get that negative out there. And then again, cosine is the one to pay attention to. Cosine is the one where the negative can just disappear. And so we'll have cosine x right there. All right. Now, another one of our main tricks that we're going to use a whole lot is we're often going to want to write things just in terms of sine and cosine. You can actually write any of the other trig functions always in terms of sine and cosine. So this cotangent here is going to be, we'll leave everything else the same here, and we'll make this be cosine over sine. And then we have to multiply by cosine here, which of course that's cosine over 1. And so over here, we're going to have cosine squared x over sine x. Okay? Well, we know anytime that we're trying to add or subtract with a fraction, we have to have common denominators. Just because there's trig functions doesn't change that basic rule. Still works the same. So I'm going to need a common denominator, which means this over here is also going to have sine x in the denominator. And so back up here, I need to multiply by sine x over sine x. And so negative sine times sine, I've got negative sine squared x. And so now that I've got my common denominators here, I can combine this together into one fraction. So I'm going to have negative sine squared x minus cosine squared x all over that sine of x. And well, I've got some squares there, so I'm hoping that might have something to do with my Pythagorean identity. If you take a look at this right here, if we multiply both sides by a negative, then I'd have negative sine squared, negative cosine squared would be negative 1. So this right here is negative 1 over sine of x. Now we know that 1 over sine x, that's cosecant. So we get negative cosecant x right here. Okay? So that's simplifying. We'll just give you an expression, ask you to use those identities as much as you can to get it as simple as you can. There's also where we ask you to verify, and that's kind of like where we're giving you the answer already. That's kind of nice, and you just have to show the work, show the steps of how to get there. So it's like we're saying, all right, if this were a simplified problem right there, then the answer to that should be sine to the fourth of x. Just show us the work, show us how we get it. All right, now you do have to just pick one side to work with. You can't work with this as an equation. You can't subtract 1 to both sides. If this was an equation, then we'd be done. It's kind of like there's a question mark here. Like, does that actually equal sine to the fourth x? You're trying to prove that. You can't work with this as an equation. Okay? Well, this is what I like to call a quadratic in disguise. This we could use that u substitution, or you could just factor it if you feel comfortable factoring it now. Again, one of the things that we are going to do a whole lot this chapter is factor these trigonometric expressions. So either just factor it yourself right away if you'd like, or if you want to do a u substitution, look at what squared gives you cosine of the 4. Well, cosine squared squared give us cosine of the 4. So if we make that substitution, we'd have u squared minus 2u plus 1. And that would be u minus 1 times u minus 1. Then we can substitute that back in. And so this is what the factorization looks like. Okay. And again, those squareds tell us, let's try to use a Pythagorean identity. Well, if we look back here, again, just be careful how you rearrange it. Cosine squared minus 1 is negative sine squared. So we've got negative sine squared x times negative sine squared x. Negative times negative is positive. Squared times squared, we get sine to the 4. And so we picked this side, we did some work, and we got it to match the other side, so we're done. A lot of times you'll see in math books, you'll see they'll put either an open box to say that the proof has been finished. Sometimes you'll see QED, it's a Latin phrase, and I have demonstrated it, but you don't have to do anything like that. One of the fun things is that you can often do these multiple ways. Same thing for the simplifying one. Sometimes there's different ways to get to the same place. This one, if you wanted, you could have started with the right side. You could have said that was sine squared, and then you could have said sine squared. Well, if I look at sine squared, try to get it by itself, that would be 1 minus cosine squared. So 1 minus cosine squared. Well, then you could have multiplied that all out and worked out of there. So there's different ways to do these. So if what you try the first time doesn't seem like it's working well for you, just maybe try something else. Just keep trying until you get it to work. Okay. Over here, this one we probably definitely want to pick that right side there. Not a whole lot you could do with the left side. Again, different ways to work with this. One way is you might see that there's squareds here, so you use Pythagoreans. You could write this in terms of sines and cosines, or all cosines for this one if you wanted. Then you'd have fractions inside fractions. You could get there, it would just be a little bit uglier. Probably the first thing to look for is if it's squared, use those Pythagoreans. So what we had here was secant squared minus 1. If you look here, subtract the 1 over secant squared minus 1 is tangent squared. So we'll take a look at this here. I've got tangent squared x over secant squared x. And so that's sine squared over cosine squared. So eventually you probably do want to get this complex fraction beside fractions. Again, one of the rules of thumb, at some point we often want to look at all sines and cosines. And so right here, what I'll do is I'll separate this out. I'll say that sine squared over cosine squared, and then dividing by a fraction is multiplying by the reciprocal. And then those cosine squares cancel out. And so we just get sine squared, which is what we were looking for. So we're done. Once it matches the other side, you know that you're good to go. There was a simpler way, actually, if you realize that there's a distributive property of division, that you can take secant squared and divide it by the secant squared, and you can take 1 and divide it by the secant squared. Well, secant over secant, that's just 1. And then just like cosine is 1 over secant, it works the other way as well. 1 over secant, that's cosine. So 1 minus cosine squared here, that just equals sine squared. So you have lots of different ways to do these here. Just kind of play around with them. Just try things. A lot of us actually find these a little bit fun, so try to have some fun with them.